Hey everybody, welcome to another remote lesson for remote learning. We're going to cover two sections because each of them are very short and kind of go over some prerequisite content from stuff you've probably seen in previous courses. So today we're going to talk about prime numbers and prime factors as the first lesson. As a reminder, a prime number is a positive integer that has no positive integers as factors other than 1 in itself. And a composite number is essentially a number that's not prime, and which means that it will have at least two prime factors. So all we're going to do in this section is take numbers and rewrite them as the product of prime numbers. So one way to take 45 is to think of it as that 45 is equal to 9 times 5. 9 is not prime, 5 is. So we're going to keep factoring the composite or non-prime numbers. And 9 is, of course, equal to 3 multiplied by 3. And then the last thing that we're going to do is any repetition of a factor, we're going to express that as a power. So 3 times 3 we're going to express as 3 squared. Moving on, we're going to do the same thing with the number 3,500. I know this is a larger number here, but it does end in zeros. So we should be able to see that that is equal to 35 multiplied by 100. Both of these are not prime, so we're going to continue to factor them. 35 is equal to 5 multiplied by 7. 100, a number, there are a lot of different ways, of course, that we could factor 100. I'm just going to take it the easy route and do 10 times 10. 7 and 5 are prime, however 10 and 10 are not, so we're going to keep factoring 10. We'll factor 10 as 2 times 5, and factor the other 10 as 2 times 5. So what we have 1, 2 factors of 2, so we're going to have 2 squared. We then have 1, 2, 3 factors of 5, so we have 5 to the third. And then lastly, we have this factor of 7. And so that would be the what we call prime factorization. Prime factorization of 3,500. All right. Oh, and by the way, what we're doing here is a reference to the fundamental theorem of arithmetic, which says that each positive integer has exactly one set of prime factors, meaning this factorization here, there's no other number that's going to have this factorization, and this is the only prime factorization of that number 3,500. Not something I'm going to quiz you on, but it's worth mentioning that this is called the fundamental theorem of arithmetic. All right, folks, I'm going to move on to the other section, which deals with the operation exponentiation, which is just, right, the power of. So x to the power of a means that we have a factors of x. Or another way to kind of think about that, x to the power of a equals x times x times x times x with a factors or a x's, right? That quantity. So one thing I'm going to ask you to do is substitute information into an expression that has exponentiation. And if you'll recall, always input things with parentheses as a good habit, okay? So we have 3 to the fourth, and we have the quantity, negative 5 squared. 3 to the fourth is equal to 81. Negative 5 quantity squared is equal to 25. And when you multiply all that stuff together, you get 2,025. All right, once again, the parentheses are important here. Make sure you're using them. You don't always need them, but it's never going to make your answer wrong. And if you don't have them when you need them, your answer is not going to be correct. All right, moving on. We're being asked to take this algebraic expression, x to the 5th power multiplied by x to the 2nd power, and we're being asked to express this as a single power of x. So x to the 5th power means we have 5 factors of x. Right, so we have 5 right here. Then we have x squared, which means we have 2 additional factors of x. And so what we have here is a string of 5 factors and 2 additional factors of x, which means we have a total of 7 factors of x. And this right here is our single power of x. So we'll leave it like that. We're being asked to do the same thing. However, things look a little different here. We have x to the 4th power being raised to the 3rd power. So if we initially take x to the 4th, what we have are 3 factors of x to the 4th. So we have x to the 4th multiplied by x to the 4th multiplied by x to the 4th. What we can then do is expand each of those x to the 4ths Now, my hope is that what you see is we end up with 3 groups of x to the 4th. So one way to think about that, of course, is we could take 4 and add 4 and add 4, which gives us x to the 12th. Or if we look back here, we have 3 groups of 4. So we can kind of think of this as 3 times 4, giving us a total of 12 factors of x. Okay, once again, we've written our answer as a single power, and so we will leave our answer as such. The last kind of thing that we'll be asked to do in this section is to take something in parentheses, like 5x, and having it being raised to the 3rd power, and we're being asked to rewrite this without parentheses. So just like in the previous problem, what we have at this point are 3 factors of 5x. Now if we take the parentheses away, right, what we have is 5 times 5 times 5, and then we have an x times x times x. We're able to reorder this because it's all multiplication. And then what we'll do to finish things off is 5 to the 3rd power, or 5 times 5 times 5 is 125, and then we have 3 factors of x, so we're writing this as x to the 3rd power. Thanks, folks. I hope everybody's doing well, and we'll talk to you soon.